Astrophotography without a telescope. In this talk I'm showing images that were taken by two members of the Bromsgrove Astronomical Society, Rob Dipple and myself, Steve Barrett. Some images were taken from the UK and some were taken from darker skies while abroad. For all of these images, the particular focus of this talk is what you can do without using a telescope. So let's start with star trails. This is the simplest type of astrophotography, but it can still give some very nice images, especially if you use a wide-angle lens on your camera. Just put your camera on a sturdy tripod and expose for a few minutes. There are no right or wrong settings to use, just try a few different settings, a few different exposures of 1 minute or 2 minutes or 5 minutes or 10 minutes and see what sort of results you get. This should work with a compact camera or a bridge camera or an SLR camera. As long as you can control how long you expose for, you should be able to get some very nice images. This particular image was a 5-minute exposure. In the center of the image there's Polaris, and all of the stars appear to be wheeling around Polaris during the 5-minute exposure. Of course, the stars aren't actually moving, it's the Earth's rotation that is causing the sky to appear to rotate. There's no reason why you don't expose for longer, but most people would prefer to take a series of shorter exposures of maybe a minute or two and then use computer software to add them all together. So here the total exposure was 6 hours, but it wasn't one long 6-hour exposure. It was a very large number of 1-minute exposures that were added together then in a computer. And there's various pieces of software that can help you do that. You can tell that this was a 6-hour exposure by looking at how large the trails are. They've all trailed about 1/4 of a revolution, telling you that this was exposed for about 1/4 of a day. Notice also that Polaris, the pole star, is close to the pole but not actually at the pole itself, and so even Polaris makes a short arc during the night. Whilst on safari in Kenya, Rob and I tried taking some star trails. My image on the left is a little bit longer than Rob's on the right, and so Rob's image shows star trails that haven't trailed quite as much, and hence there's more detail to be seen in the Milky Way that's running from top to bottom in these images. We simply went out at night and took these images over the top of our large rooftops and some trees there. So if you want to capture more detail, you can see the longer you expose for, if you allow the stars to trail, that will blur any detail in your images. So if you want to capture more detail in your astrophotos, then you need to move the camera so that it follows the stars as the Earth rotates. This is where a star tracker comes in. So to make the most of the beautifully dark skies in Kenya, next time we went on safari, I thought what we really need is a star tracker. So I built myself one as a little DIY project. I tried to make it as simple and as cheap as possible. If you're interested in building one for yourself, there's a link at the bottom of the screen that shows you how I constructed this particular model. If you happen to have the bits lying around, you might be able to do it for free. Otherwise, it might cost you 20, 30, 40 pounds to buy all the bits to make one for yourself. This is what's called a barn door tracker, because it simply moves one arm, the top T, relative to the bottom. You can see the movement. If I lift up the top arm, you can see that there's a pair of hinges at the back there, so that the top arm moves relative to the bottom. And this pair of hinges defines the axis of rotation. And this little white tube here means that if you simply look down the tube until you can see Polaris, not quite lined up with the pole, but close enough to take a lot of different images, then by simply eyeballing Polaris through that tube and adjusting this particular star tracker, then as long as it drives at the right speed, and that's determined by this motor down here and a pair of batteries and a little potentiometer and some resistors to make sure that the speed at which this motor drives is such that when this little nut moves up this thread, then the top arm of the tracker moves at just the right speed to compensate for the Earth's rotation. Here's an example of what it looks like if you switch the tracker off and take an exposure, then the stars will move. But at the same time, I took another exposure of the same length, but this time with the tracker switched on, and if it's lined up correctly, then the tracker will move the camera to follow the stars, and so the stars will then be pinpoints. So not only is this aesthetically more pleasing to have the stars look the way they should, as pinpoints rather than short lines, but it also means you can see more detail. For instance, down here in the bottom right of the image, the stars have trailed and it's difficult to see what's going on, but here you can see there's quite a few faint stars in that region. And these stars are more visible here simply because for any given star, the light is now falling into 1 or 2 pixels, whereas when the stars were trailing, the light was being smeared out along a line, and so the faint light from the star was even more difficult to see. So by using a tracker, you can expose for longer, the stars will stay pinpoints, and you will see more detail. So one of the earliest pictures I took after I built this tracker was this one. It's an image of the Milky Way. And from now on, whenever I show an image, down at the bottom of the screen, I'll show who took the image, which camera was used, what particular lens was used. In this case, it was a wide-angle 35mm lens, and how long I exposed for. So just like before, rather than giving a long 20-minute exposure, I decided to take, in this case, 20 1-minute exposures, which amounts to the same amount of light being captured by the camera. But by taking a series of shorter exposures, that gives you a little more flexibility. If you have 20 images and one of them happens to be spoilt by an aircraft going by or a little bit of clouds coming by, then you can simply not use that particular frame, that particular exposure, and add the other ones together to give you essentially the same effect. So here we see essentially the heart of the Milky Way. This is the centre of the Milky Way, our galaxy, and you can see a few different star clusters, a few different nebulae, stars of different colours, etc. You don't have to build one for yourself. If you are adept at these things, then great, you can build a tracker for yourself. But if you would prefer, you can simply go out and buy one. For instance, a little while ago, I bought this one, an Ioptron Sky Tracker. Other makes are available. There are 2 or 3 or 4 different companies that make star trackers. What's inside? Well, effectively in this white box, it's really just a motor. That's all it is, a small motor that is driven by a set of electronics that makes sure that it's moving at just the right speed, such that with this worm and wheel, this wheel here will rotate. This is what the camera is connected to. This will rotate at 1 revolution per day, 1 revolution in 23 hours, 56 minutes. So providing the tracker is aligned with the Earth's axis, that speed of rotation will ensure that the camera then tracks the stars. How do you ensure that the tracker is lined up correctly with the Earth's axis? Well, that's why there's this little polar scope on the side here, just like you find in some polar scopes in mounts of telescopes. So how do you know where Polaris ought to be? Remember, Polaris isn't actually at the pole itself, it's slightly offset. So where should you align Polaris? Well, there's an app for that. You can simply install an app on your iPhone or your Android phone, and using that, the app will work out what the date and the time is, and it'll use GPS to locate where you are in the world. And from that, it'll determine where Polaris ought to be in the field of view that you see in the polar scope. So here the North Pole is in the centre, and this is telling us on this particular date, at this particular time, Polaris ought to appear where this green dot is showing here. So you simply move the sky tracker on your tripod until Polaris is in the position shown there, and then the tracker should be lined up with the Earth's axis. The camera is simply bolted onto the tripod bush here. The tracker is usually bolted onto a tripod. The camera is then bolted onto this tripod bush. And once you've lined it up, then you're good to go. You can see a few cameras here, whether it be wide-angle lenses or telephoto lenses. It is common to use something like a ball and socket joint there, just to allow the camera to point at any part of the sky whilst the tracker is doing its job. This particular image was taken with a very wide-angle lens, a 10mm focal length lens, and so the image covers a lot of the Milky Way. The centre of our galaxy is close to the bottom of this image, which is tricky to see in the UK as it's low in the south during the summer months. This particular image was taken from the lower latitude of Tenerife in the Canary Islands, and so we can see rather further south more clearly. If we think about this region down here, which is where the centre of the Milky Way is, the centre of our galaxy, if we were to switch to a larger focal length, a longer focal length, then we would see that area shown in red in greater detail, and I can show you that here. So there is the result of taking an image with an 85mm lens. Again, you can see from the bottom a whole series of shortish exposures, in this particular case 2-minute exposures, and I added 10 of them together to get the equivalent of a 20-minute exposure. But with the 85mm lens, you can see that it's showing more detail in the dust lanes of the Milky Way and a little more detail in these nebulae, the Lagoon Nebula here, the Trifid Nebula, a little bit of pink and blue showing there, and various star clusters and other nebula visible in the image. If I go still further to a 135mm telephoto lens, then we can actually see even more detail in star clusters or nebulae or galaxies, whatever it is we're interested in. And also we see that long exposures can bring out the colours of stars that are otherwise rather difficult to make out with the naked eye. So in this particular case, this is the red giant Antares. It's looking a little bit yellow here, but that's the star Antares, the brightest star in the constellation of the Scorpion. And you can see that other stars are illuminating the nebula here, so we're getting a little bit of nebulosity that's yellow or orange, a little bit of nebulosity that's blue, produced by this blue star, and also you can see that some dark nebula as well that are obscuring some of the light from more distant stars. That's just an indication of what it is we're looking at. A few different stars. We're also picking up a globular cluster, a very large number of stars in a very compact region of space. And this region is called a cloud complex because there are lots of nebula and lots of stars illuminating those nebula. If we come back to the UK, this image was taken by Rob from his back garden. You can see that even from the UK, a relatively short exposure can still produce a huge number of stars. In this particular case, this is looking at the Milky Way as seen from the UK, and it's perhaps difficult to make out the constellation that's in this image. Perhaps it's familiar to you, but it's very difficult to see simply because there are so many faint stars that are caught by, in this case, a series of 30-second exposures. If I draw some lines joining the brighter stars, perhaps you can make out this constellation. There we go, there's the W of Cassiopeia. Another of Rob's image, this time taken from a campsite in the New Forest. Being away from urban streetlights and close to the south coast of England, this allows a better view of the Milky Way, stretching down to the constellations of Sagittarius on the left and Scorpius on the right. Because the camera is on a tracker and so is following the stars, that means the stars are nice and sharp, but any objects in the foreground, such as the silhouetted trees, they will appear blurred. That's a natural consequence of using a tracker as the sky rotates. Also from the New Forest, this was an image Rob took of the constellation Andromeda and includes the Andromeda Galaxy. If we crop the image, we see that we can actually see much more detail, and this is a reminder that you don't necessarily need to use a telephoto lens. This was taken with a standard 50mm lens on his camera, and even there we can see detail inside the Andromeda Galaxy. We can see the nucleus, we can see the spiral arms. Taken in 2017 at a Bromsgrove Astronomical Society star party, so again a reasonably dark sky site. This image by Rob shows the pink Lagoon Nebula and the pink and blue Trifid Nebula, as well as a number of other star clusters within the field of view. At a more recent star party, I took these images now with a 300mm lens, so we're getting to a somewhat longer focal length. I would advise that 300mm is probably about as far as you would want to go on the sort of tracker that I'm talking about here. So at these longer focal lengths, you can see, of course, more detail in, for instance, star clusters like the Pleiades in the top left, nebulae such as the Veil Nebula in the top right. This is the remnant of a supernova that went off thousands of years ago. And there you can see, not only can you see structure in the supernova remnant, you can also see some colours as well, which is very nice. And the image in the foreground at the bottom there is again the Andromeda Galaxy, and again you can see detail in the spiral arms by taking exposures. In this case I took a series of 60-second exposures, and typically there's 10 or 20 exposures in these images. One of the nice features of using a star tracker for astrophotography is that they are not limited to use in the UK. They are small enough and light enough to be slipped into your holiday luggage to make the most of any dark skies that you might have elsewhere in the world. But there is a little bit of a catch. These star trackers work best when you can set them up and align them using Polaris, which is fine in the UK. But for instance, if Rob and I go to Kenya for a safari and we would like to take pictures at night, Kenya is on the equator. So that's going to be a problem. Trying to line up on Polaris when you're on the equator is rather tricky. And we can see that if we think about where Polaris is. The North Celestial Pole and Polaris right next door to it are essentially directly over the North Pole of the Earth. So at a latitude of 50-something degrees from the UK, between, let's say, 52, 55 degrees, then Polaris is fairly high in the sky. The altitude of Polaris is actually equal to your latitude. The altitude in the sky is equal to your latitude. I said it right in the first place. And so if we're here in the UK, then it's relatively easy to line up our tracker or our telescope. But if we're here on the equator in East Africa, then the North Celestial Pole and Polaris are essentially on the horizon, and hence will be hidden behind elephants or hills or something else. So we have to find a different way of making sure our tracker is lined up. So we could, for instance, use a compass and a spirit level to make sure that we're in the right direction. The compass will tell us that we're pointing north, and the spirit level will tell us whether or not we've got the latitude correct. If we are 2 degrees away from the equator, then we need to make sure that the tracker is tilted by 2 degrees. Remember, the altitude of the pole is equal to your latitude. But be careful, magnetic north is not the same as true north, so you have to be wary of that. And also a compass needle can be affected by nearby metal, such as, for instance, found inside trackers. So you do have to be careful if you're using other methods. Another alternative is you can get an application for your phone or your tablet which tells you where the stars are at a particular time. So for instance, if we were looking north and we can't quite see Polaris, in this case we're just south of the equator, and so Polaris is just below the northern horizon. It would be approximately where the N is of this compass point here. But we can use the app to say, for instance, I can see the stars in the Plough here. I can use the app to say, well, when is this particular star due north? And then if that is at, for instance, 9:10 in the evening, then I wait until 9:10, and then I know that that star is due north, and I can use that to tell me which way I need to point my tracker. So there are alternatives. And although aligning a star tracker on the equator is more awkward than doing the same in the UK, the rewards can be spectacular. So here's an image taken by Rob. It's a mosaic of quite a few images taken with a 50mm lens. He took 20-second exposures, 10 of them for each of the images that he wanted, and then made a mosaic of the whole thing. And you can see wonderful structure and detail inside the Milky Way itself. There's a red giant Antares in the constellation of the Scorpion, the constellation of Sagittarius over on the left-hand side. And again, we can see various nebula and star clusters embedded within the Milky Way. What looks like a bright star here is actually Jupiter, and again, over here, this is the planet Saturn. Not to to be outdone, I wanted to get an image like that as well, so I used a slightly different lens. I used a 35mm lens, a slightly more wide-angle lens, which means that I could get the same coverage of sky in fewer images, and so I used about 4 or 5 images here to make this particular mosaic of the Milky Way, again catching the centre of the Milky Way galaxy and Jupiter and Saturn in there as well. Taking a slightly different way of constructing the mosaic, I just produced a little more detail in that central region, again with Antares, the brightest star in Scorpius, and there's the very bright Jupiter, and there's Saturn over on the left-hand side. But by making a mosaic, you can either add lots of them together to get a very wide angle, or you can just take 1 or 2 images to concentrate on a particular field of view. You might say that if we're not using a telescope, aren't we limiting ourselves somewhat? For instance, maybe we can only see some fairly close objects if we're using a camera but not using a telescope. So you might ask the question, what is the most distant object that you could possibly hope to see with a camera? How far away is the furthest star, or more likely the furthest galaxy, that you could possibly see before you start thinking about, well, do I want to pay money for a telescope? Well, the furthest object that you can see is probably further than you think. I tried taking this image of a very distant galaxy. In the bottom left you can see the setup I used. There's my camera with a telephoto lens, and the camera and lens are bolted onto the tracker that I showed you earlier. I then made sure that the tracker was lined up by pointing it at Polaris, and then pointed the camera in the constellation of Draco, as shown by the top left inset and that little rectangle shown there. The main image that you can see here is the image that I took, a relatively long exposure. I took a large number of 30-second exposures to produce that image, and I was hoping to catch a very distant galaxy in the middle of this region. And I'll blow that up in the top right so you can see it a little more clearly. That object there, indicated by those 2 grey lines, that is a very remote galaxy called a quasar. And I checked what its distance was by checking with professional surveys, and found that that object is 25 billion light years away. It is an incredible distance. And this image shows that, even without a telescope, a camera can capture the light from a galaxy many billions of light years distant. This light has been travelling for much longer than the Earth has even existed. That's quite a thought. And it's a reminder that if you want to do some astronomy or some astrophotography, you don't need a telescope. Thank you for listening.